All right, well, we're beginning Module 9, Chapter 8, which is dealing with sampling distributions, because not everything that we see in life is going to be individual toddlers. And to give you an idea, if I were to give you a thought experiment, if you wanted to find out how much a penny weighs, would it make sense to take a penny and weigh it? Why not, right? Well, what if you've grabbed a penny that is a little bit lighter than normal, or a penny that's a little bit heavier than normal? And not only that, do you really have a scale that is that precise to measure down to the accuracy that you need? Does it make sense in many different ways to maybe grab 10 pennies? Because the chances of you grabbing 10 pennies that are very light or 10 pennies that are very heavy is going to be not very likely. It's more likely that you get a random spread of these that cover light ones, heavy ones, but most of them normal ones. And you can weigh all those together, divide by 10, and you'd have your average weight. That is a much more accurate way of measuring the weight of a single penny as compared with weighing a single penny. So that's what this chapter is going to be about, the distribution. And we're going to do this one section at a time, right? This first of all is the distributions of the sample mean. And boy, the vocab gets pretty crazy in this. Distributions, a distribution, like a normal distribution. The sample mean, not the mean of the population, but the mean of the sample. And we're going to find out that, well, I've already talked about this. And you've got the slideshow again loaded up in your, I think I'm going to put it in both the Pioneer Google page, but also the Canvas page here. So feel free to read through these as you go. But if you're going to take a sample, maybe that sample of 10 pennies that I already took, that sample has a mean, has an average, has a mean to it. Well, what if I grabbed another sample? I would have a second mean. Even though I've already grabbed 20 pennies, I only have 2. So what if I grab a third set of 10 and find its average? What I'm doing is I'm building a set of samples. They become a population in and of themselves. So that's what we're going to do in this first thing. We're going to describe the distribution of the sample mean, and that's with a normal population. So statistics such as the x-bar, the sample mean, are random variables since they vary from sample to sample. And there's going to be a probability distribution associated with those. The sampling distribution, these are the same ideas as last chapter. The sampling distribution of a statistic is the probability distribution of that sample. And the sampling distribution of the sample mean x-bar is the probability distribution of all possible values of that based on a particular sample size of that handful, right? So going to penny sizes. Did you know that the weight of pennies minted after 1982 are normally distributed? And they have a mean, the population has a mean of 2.46 grams with a standard deviation of 0.02 grams. Well, what if I had this big, huge jug of pennies in front of me? And I took groups of 5. I don't know why we don't do 10. 10 makes better sense, right? But what if I just took a sample of 5 pennies, and I weighed those 5 pennies? For instance, the slide in the next. What if I take a handful of 5, and what if I weigh each of those 5 pennies and get those values? Well, then I could add those, divide by 5, and find out that the mean is 2.479 for that one sample. And then I could find the other 199. And again, what this table represents is not 200, was it 200? Yep, not 200 pennies, but actually 1,000 pennies weighed in chunks of 5 at a time. Now, what's going to be interesting is if we treat those 200 samples as individuals, I can compute the mean and standard deviation of those samples. So let's consider this. This is the population given to us by the U.S. Mint. The population mean is 2.46. Well, guess what our sample mean is? Those 200 samples. If I add those all up and divide by 200, guess what I get? The exact same thing. That's not surprising, right? If I'm going to weigh a whole bunch of pennies and find out their average weight, they're probably going to be the same as what the government says. But the individual pennies have a standard deviation of 0.02, 2/100ths. But the sample means, look at the difference in that standard deviation. It's much smaller. Why? In fact, here's a histogram of this. These are the weights of those pennies. You can see that it's pretty normal looking. But why is the standard deviation so much tighter? Well, as I kind of described in that first example, if I grab one penny, it might be light. It might be heavy. It might be normal. But if I grab a handful of them, there might be a light penny in this handful. But am I going to recognize its lightness or heaviness? Probably not. That one penny that's maybe a little bit more towards the extremes is going to be tempered by the other 9 pennies that are probably not surrounding it but are spread throughout. So any of those individual outlying or extreme values is going to be lessened in its effect. So we can see that the standard deviation gets much smaller. The size of n plays a huge role in this. And again, the size n is not the number of samples, not 200, but the number of pennies in each sample. N equals 5 in that first one. Maybe it seems then obvious as the size of the sample, 5, 10, 15, as the size of the sample increases, the standard deviation is going to decrease. This is gonna hit you several times on the quiz. Not as much on this particular quiz because they're all samples, but really focus well on this when it comes to the test. The population standard deviation is going to be different than the sample mean standard deviation. So how much does it decrease? We'll get to that. What if we grab 20 pennies in each group instead of 5? Will anything change? What if we grab 200? If we grab 200 samples of size n equals 20, we're still going to have that same mean weight of 2.46, but now instead of 0.02, instead of 0.009, we now have 0.005. It's getting tighter and tighter together. And is it predictable to find out what that standard deviation is? And yes, it is. Here is the formula that you're going to use. I'm actually going to write that over here on the board so we don't forget it. But the mean of our the population standard deviation of our sample means is going to be the stated population standard deviation divided by the square root of the sample size. Interestingly, this was always true even when our sample size was 1, even when I took 1 penny at a time, because the square root of 1 is 1, and the population standard deviation divided by 1 is going to be the same. But whenever I have a sample size that is greater than 1, my standard deviation is going to be cut down. It's going to be shrunk down because, again, I'm tempering those small or heavy individual members by having a group of them. So remember, if you've got a sample size of things, divide that by the square root of that sample size. All right. And then, and then once we have the new standard deviation, knowing that the mean is going to equal the mean, we can then use our stat crunch, our normal CDF, the tables, whatever we want, to figure out what proportion is within a certain amount. So we could have an example here. The weights of pennies minted after 1982 are approximately normal distributed, 2.46, 0.02 grams. Those are stats we already stated. What is the probability that a penny selected at random has a weight of at least 2.465 grams? What is the probability that a simple random sample of 10 pennies has a sample mean weight of at least 2.465? What is this question asking? Well, this question is saying 2.46 is the average, 2.465 is above average. What's the chance that a single penny is going to weigh 2.465? And we could use some normal analysis with this. Well, then what is the probability that a simple random sample of 10 pennies, what if you grab 10 pennies, find its average to be 2.465? Well, we would have to do the math to figure that out, and let me do that for you.